Welcome to the AMD Embedded Solutions Training Module, Differentiating Through Innovation, an introduction to AMD Accelerated Parallel Processing Technology. First, let's define the two types of multi-core processors we will be discussing. The most common type is the homogeneous multi-core processor. In a homogeneous multi-core processor, each of the processing cores are identical. This is the case with traditional multi-core x86 CPUs that now have between 2 and 16 x86 processing cores. In contrast, the heterogeneous multi-core processor has multiple processor cores, which are different from one another. This diagram represents a heterogeneous multi-core processor with 4 x86 cores and 80 graphics processing cores. Now let's look at the evolution between these two types of processors. This chart illustrates the evolution of CPUs. The graph on the left shows where we started with single-core processors. Over time, their performance increased, but with those increases in performance came increases in power and complexity of the core architectures. To manage those increases in complexity and power, architects began putting multiple cores into a processor. This enabled solutions to access greater performance without significant increases in power or chip complexity. However, the transition to multi-core software architectures took some time. Presently, multi-core software architectures have developed to enable the realization of the available performance and the scalability to many cores in a processor. But we are again running into the power limit and number of usable x86 cores that can be put into a single processor. The next evolution cycle begins with the transition from homogeneous computing to heterogeneous computing. The graph on the right shows where we are on the performance curve for heterogeneous computing. We are just beginning to move up the performance curve and beginning to realize the performance and efficiency gains that can be realized by a heterogeneous architecture. The current challenge lies with the programming models available to develop software for a heterogeneous solution. Even those challenges are being overcome through software solutions such as OpenCL and Direct Compute, which we will talk more about. What about the GPU? How did we get to where we are today? GPUs by design have always provided very good throughput, and over time they have become more programmable with the transition from driver-based programs to system-based programming models for graphics. And today, with OpenCL and Direct Compute, going beyond just graphics processing to programming the GPU for system-level applications is a reality. This is where the CPU and GPU evolution have come together into the new AMD Fusion family of APUs. Let's back up a little to give you a better understanding of what an APU is and how it came to be. Current PC architecture is built around the highly flexible x86 architecture of the traditional CPU. It has evolved over the years, going from a basic engine to the multi-core processors that we enjoy today. This has allowed PCs to become increasingly efficient at dealing with multiple problems in parallel. As fast as they are, on their own, today's CPUs lack the performance to deliver a vivid, modern computing experience. Fortunately, like the CPU, the GPU has also come a long way, and innovative architectures and tools have emerged that are better suited to harness the power of GPUs. The GPU has evolved from a basic device to render an image on the screen to the advanced 3D graphics processors that drive the rich visual interfaces of today's PCs. Today's GPUs are built around an advanced parallel processing architecture, which is capable of operating on hundreds of pieces of data in parallel in a single cycle. Software tools like Direct Compute and OpenCL permit developers to create standards-based applications that combine the power of CPU and GPU cores. At the center of all communications lies the Northbridge controller, which handles communications among the CPU, GPU, RAM, BIOS, and the Southbridge controller. Each architecture has its strengths and weaknesses. Neither alone will be able to address the complex problems that will challenge PCs in the future. Enter the Accelerated Processing Unit, the APU. Taking embedded computing to a higher level, APUs are the next generation of AMD processors. With the combined power of AMD CPU technologies and discrete-class DirectX 11 capable AMD Radeon graphics in a heterogeneous computing architecture. It's the best of both worlds. Their enhanced processing power and power efficiencies enable new levels of performance through parallel processing in small form factor and fanless embedded applications. There are numerous applications that can benefit from this new architecture. Applications that use sensors to capture large amounts of data and must analyze, manipulate, and quickly act on or output the results are great examples of applications that will, and in some cases already are, taking advantage of this new heterogeneous computing architecture and AMD Accelerated Parallel Processing Technology, APP. For example, the Ximia Carrera G camera is leveraging an AMD Fusion APU to deliver 90 gigaflops of processing power to tackle the toughest machine vision system applications, compared to their previous version that delivered only 2 gigaflops of processing power. In medical imaging, parallel processing has been used to accelerate the FDK algorithm, which is widely used for tomographic reconstruction of X-ray CT scanner data. To improve analytics and automation in digital signage and surveillance applications, companies have developed algorithms to identify whether the subject or audience is male or female, and whether it is a child or an adult, and they are working on accelerating the analysis of this image data through parallel processing. One company is working on using parallel processing to replace a DSP for processing millimeter wave data to find improvised explosive devices in the ground. Similar things could be done to replace DSPs in telecommunications and mobile radar imaging. Evaluations are ongoing that leverage parallel processing for deep packet inspection. With AMD's award-winning HPC solutions and our continued advancements in GPU stream technology, AMD continues to enable HPC customers and partners around the world with powerful, well-balanced computing solutions for demanding HPC workloads. And recently, Penguin Computing installed the first HPC cluster using AMD Fusion A-series processors at Sandia National Labs. Most compute-intensive applications involve sophisticated algorithms with specialized mathematics. These algorithms can stress even the most powerful multi-core CPUs, resulting in increased latencies, compute times, and power dissipation. Using the highly parallelized architecture of AMD's SIMD engines can greatly improve performance. Customers want to focus on application development, not on creating custom hardware and development environments. They can now leverage off-the-shelf, programmable, board and system solutions and standards-based software environments to quickly develop innovative new applications. And the volume of domain-specific OpenCL libraries is growing rapidly, enabling developers to leverage these into their applications. AMD Embedded Solutions has introduced OpenCL-compliant products in a wide range of power and performance options to enable parallel processing applications. The AMD Embedded G-Series APU offers an excellent combination of single or dual-core low-power x86 processing and an 80-core GPU to enable low-power or small form factor applications to extend their performance through parallel processing, without adding additional power or cost to the system through external devices. As well, AMD Embedded Discrete GPUs offer a range of options in chip or board-level solutions. These solutions offer excellent parallel processing capabilities, ranging from 192 gigaflops to over 1.3 teraflops. There are a number of standard off-the-shelf boards built around AMD APU and discrete graphics technology that support AMD Accelerated Parallel Processing Technology. For a listing of these board-level solutions, please visit the AMD-based Embedded Product Catalog and select Accelerated Parallel Processing from the application list. The listed solutions can be sorted by form factor, processor, or application. AMD offers extensive resources to help developers learn how to begin developing software for parallel processing applications. For webinars, tutorials, the AMD Accelerated Parallel Processing Software Development Kit with support for OpenCL, including samples and demos, and development tools, please go to AMD Developer Central at developer.amd.com. Whether you're just evaluating how parallel processing might help to improve the performance of your application, or looking for a starting point for software development, there are several sample applications included in the Accelerated Parallel Processing SDK. You'll also find samples for AES encryption and decryption, discrete cosine transformation, fast Fourier transform, matrix multiplication, and much more. Also available for customers to reference is the AMD APP Developer Showcase. It is an exhibition of notable applications and demos created by customers and technology partners using AMD APP technology for a wide variety of applications. These include physics, video processing, scientific simulations, finance, and medical imaging. Thank you for taking some time to learn about AMD Accelerated Parallel Processing technology and the resources available to help your customers get started. For a link to the public version of this presentation, presented in collaboration with Themis, please go to the AMD Embedded G-Series webpage